Thank you very much, Andrew, for your kind and generous introduction. It's a pleasure for me to be here. I'd like to thank Dr. Said Zuhdi and Dr. Khaled Manema and their team for organizing this conference and giving us a chance to get together. It's a pleasure and honor for me to be here. As you can see from the title of my talk, I'd like to give a progress report of one of the areas of research activities in my group in which we would like to see how we can use metamaterial and metastructures in order to do analog computation with wave. 2 years ago at this conference, which was held in Paris, I gave some of our results at that time, how metamaterial can actually help to do, for example, equation solving and to actually make matrix inversion using electromagnetic waves. Today, I'd like to give you progress reports that I mentioned in what we have been expanding our work in the past 2 years. But first, let me show you one slide to refresh your memory of what we did in the past. So about 10 years ago, we came up with the idea of how we can actually design metamaterial that would do mathematical operations with waves. Shortly after that, we came up with the idea to how to design, using the inverse design, a metamaterial that when the wave goes through them, you can actually solve integral equation, the Fredholm integral equation of the second kind. And the structure that you see based on the inverse design, we called it Swiss cheese metamaterial, and we built that system in the microwave domain. Shortly after that, in a collaborative effort among the three teams of Andrew Alou, Albert Coleman, and my team, we joined forces and we brought that concept into the nanoscale in optics. And that was in 2023. Now, in the past 2 years, we have been expanding this concept in several different directions. So let me share with you some of them today. One of the directions that we decided to push our work is in the area of how metamaterial can actually help us in vector matrix multiplication with waves. Why are we interested in vector matrix multiplication? Actually, what we did for the equation solving and inversion of a matrix already has vector matrix multiplication there as well. As you know, in the area of artificial intelligence, machine learning, and deep neural network, vector matrix multiplication is one of the fundamental mathematical operations that is there. And we wanted to see how metamaterial can contribute, if any, to the area of AI and machine learning. And of course, as you know, last October, the Nobel committees gave Nobel Prize in physics and chemistry for the foundational discoveries of the areas that relates to AI. So as I mentioned in our previous work, we had already shown how we can invert a matrix, and that inherently has something about vector matrix multiplication. So in order to expand that, we decided to do the following. Rather than using the similar platform that we have done in the past, we decided to bring this concept into the silicon photonic plane. The reason we decided to do that is because then it becomes mass producible. So in collaboration with my colleague Firouz Aflatouni at Penn, we decided to actually do two things, to design two surfaces on the silicon photonic platform that can do vector matrix multiplication at the wavelength of 1.5 micron. And I'm going to talk about one of these two platforms in the interest of time, how we designed it and what ideas we had behind it. So let me show one of these structures that we have over here, which you can see here. What you see over here is the top view of the design that we have in order to do this matrix multiplication there. Just to give you an idea, this is about 34 micron, this is about 23 micron. And this, because we wanted to do it, by the way, in silicon photonic platform, remember in the Swiss cheese structure I showed you in our previous work, that had two materials. At that time in the microwave, the two materials we had was one dielectric, the other one was air. But when we wanted to bring that into the silicon photonics, we didn't have a luxury of using two different materials. So we said, what else can we do in order to create an index contrast to achieve this matrix multiplication? And the way we did it is the following. As you see over here, the pink region is a region with the silicon with 220 nanometer, a standard silicon insulator. But the lighter region that you see over here is also silicon, but that one is 150 nanometer. In other words, we try to etch the region using the method of inverse design in order to create this inhomogeneous in geometry structures. Now, because this silicon has a guided wave structure through this, with the change of the thickness, you have effectively different mode index. And that different mode index help us actually create this system that can do vector matrix multiplication. And the chip was designed and the foundry that made it for us. And then we did the experiment, and indeed it worked. So this is exciting for us that we can do this. But you may say, okay, this is fine, but this is only 3 by 3. If you really want to have this one there, we have to increase the number of input and outputs. And that's a very valid point. How do we actually scale this system? In order to address that problem, oh, by the way, let me show you actually the photograph of the chip. Here you can see this is actually what's really happening over here, of course, with the grating coupler and photodetectors. This is the zoom version of this that you can see, and eventually you get to this structure, and this is effectively that Swiss cheese structure I was mentioning to you, but now on the silicon photonic platform. Our work was selected as one of the highlights of optics and in the OP and optics and photonics news. How do we make this thing larger? Well, one way that we can do this thing larger, of course, again, use a brute force of inverse design and to make that. Here is an example of a design that we have for the 10 by 10. Now, we haven't built this. This is just to show that inverse design can do that. But of course, naturally, as you increase the number of input and output, making the inverse design to create that becomes harder and harder, become more time consuming. While this could be a possibility, but we said there should be another way that we can solve this problem. So we actually go and look at the class of matrices that would be useful for certain class of applications. And these matrices are banded matrices. These are block diagonal matrices that would be quite useful, by the way, as a convolutional matrix, particularly for the imaging application. So you're all familiar, by the way, with the banded matrix and with the black diagonal matrix that you see over here. So the size of this matrix could be as large as you want. But of course, the number of degrees of freedom is limited, and that's the block that we have there. So in a sense, we were thinking more kind of like an inspiration from biology, that if I actually have a stem cell, can I put this thing next to each other and create a larger and larger system? In other words, can I have a system that I can design only one element of this using inverse design, and I put them next to each other, as many as you want, in order to create the matrix multiplication you would like to have. And indeed, that's possible, by the way, for the banded matrix. One of the things we decided to do is to apply this to a couple of examples. One of the example we try to apply this is a wavelet transform, which is, of course, quite a useful transform, by the way, in imaging. So here we decided to design a system, as one of the members of my group, Brian Edwards, did, to have a system that using the inverse design, you design one unit of that, and then you put it next to each other. What you see over here is, again, something like a silicon photonics. The blue region is SiO2. The green region is silicon with a thickness of 150 nanometer. And the brown region is also silicon with a 220 nanometer. This system, by the way, actually would do wavelet transform when you actually bring the input to this system. And this is a computer simulation we have. Let me show you another computer simulation that we put these things next to each other. This is 31 units that we put next to each other. These units are all identical in geometry. However, the field distribution, obviously not identical. If you actually put this input, this complex input into this structure, then the output that you see over here is going to give you the strength of the wavelet 1 and wavelet 2 element there. You notice that intentionally this one that we put over here is a higher spatial frequency here, lower spatial frequency here. You see the wavelet number 1 is more over here compared to wavelet number 2, and of course the role flips over here. But that was a computer simulation. So we decided to build this. So again, we put that on silicon, and in collaboration with my colleagues, Firouz Aflatuni, this is the structure, the design of the structure that we built. This is a top view of the chip. Let me walk you through this to see what we see over here. This is about 45 to 50 micron, and this is about 20 micron in width. This is a cross-section that you see over here. The darker region is the silicon, again, with the 220 nanometer. The lighter region that you see over here, again, silicon with 150 nanometer. And you notice, by the way, every two of these repeats over here, and that was necessary for our wavelet transform design. And if you look at the side cross-section of this, and this is the cross-section that you can get from here, this is 20 micron that you see over here, you notice clearly the thickness varies. And that's the cross-section we have over here. I'm going to show you the experimental result, but first, let me show you the simulation that we have over here. Quite interesting, by the way. You put this input, you see how the field actually propagates through this system, through this, single mode, slab that goes through this. And what comes out, it will give us an indication of the strength of the wavelet transform that we have there. So this is the chip that we built. It's about 1 millimeter you see across here in the image that you see over here. This is the schematic of the chip. By the way, this chip has 4 parts. I mentioned to you about the wavelet transform, but we did another transform there too, which I don't have time to go through that. And that's a fractional derivative transform, which is a very interesting, operation for some of the aspects of filtering. You notice that these 4 parts, the wavelet here gives us the amplitude, which I'm going to show you, phase over here, and this is the fractional derivative part. Today, I'm going to talk about this part for you there. So this is the top view of that. You have these grating couplers that will bring the light into your system. This is actually that little surface that's designed in large, shown over here. This is the one that would do wavelet transform. And you notice, by the way, the outputs coming out, and that 5 of those outputs go to the photodetectors, the photodiode that we have over here. Let me explain the color coordination over here that we have over this. These are we showing over here. This color, of course, don't have any meaning with regard to the wavelength. It's just to show you the plot that I show you over here. It's the output at what. So now I'm going to show you the simulation result first. Every row is when you illuminate the grating coupler of one of these. So first row is when the grating coupler 1 is excited, and the second row when this one is excited, and so on. And then you see, by the way, 5 colors over here in that bar. This color relates to the value or the magnitude of the output that we get from here. You notice when we excite this one, of course, these 2 is more excited compared to the other one. That's what these 2 color, and there are 3 other ones almost 0. As you go to the other grating coupler, then you can see that these things will come over here. But that's a simulation. And this is the experiment. So the agreement is very great. And we were very pleased to see this. Actually, we literally did it recently. It's about 6 weeks ago, 7 weeks ago that we have that one there. You notice that in this part of the chip, we actually measured the magnitude. But we also wanted to measure the phase. And of course, measuring the phase in light is quite challenging. We have to do it with interference. So another part of the chip, actually, we create these Y junctions that we have over here. We designed this Y junction that gets, by the way, the output of this and interfere them. And then we can measure the result of the interference there. And that would give us an indication for the phase. Again, this is the simulation result that we see over here when you excite this grating coupler there. And this is the experiments that we have there. This is just, right half of the press is about, 6, 7 weeks old. And right now we are working to do more and do the manuscript on this as well. So we're very excited about this. That indeed this structure, this metasurface can do that, and of course you can do other transformation as well. But at the same time, we know that when you have the silicon photonic platform, obviously the real estate is a commodity. And we would like to make the advantage of every single area on the photonic chip. We decided to see what other way we can actually take advantage of the area. So that's what we decided to look at this theoretical work that we are working on. And that is, would it be possible to actually think about a metasurface in which we would do certain functionality, just like wavelet transfer I mentioned to you, just like, vector matrix multiplication I mentioned, but at the same time, that chip can do other things as well. So what is the general idea we have? Imagine that you have a 3-dimensional cube, just as a conceptual idea. Imagine you have a 3-dimensional cube, and you would like to use the inverse design to design this cube that will give you 3 different functionality independently. For example, when I have 3 different matrices embedded in this single cube, such that when I illuminate an input in this direction with the arbitrary input, the output that I get over here would be vector matrix multiplication with the matrix K1. K1 is the one you decide what it is. At the same time, the same block, if I illuminate it from the other direction, that give me a different matrices independent of the first one without a crosstalk. It's very important, without a crosstalk. Of course, the third one as well. But that's a tall order. Can inverse design actually give us this system that we can do that? So I test this idea theoretically on a two-dimensional silicon photonic aspect. So now imagine we go back to the 2D again. Imagine that you have this system and you would like to actually design the index of, the effective index that you have over here, such that when you have the 10 input over here and 10 output, that will be one setup matrix, K1. With the same real estate, you can use it when you have another input, that output that's coming over here. Intentionally, we use the number of input and output here different than this number of input and output. So can we do that? So in order to do that, again, we were thinking for the future to have this in silicon photonics. This is just the theory right now. We haven't built this. So we said, okay, what would happen if we actually look at this system? Again, same thing as a silicon photonics. Imagine you have a thickness of 220 nanometer again, and this would be the red region that you see over here, and another thickness 90 nanometer, and that would be basically the yellow region over here. Would we have this distribution of H area such that I can achieve these two different vector matrix multiplication independent of each other? The answer is yes. Actually, on theory, it's possible. Like I say, we haven't built this yet. So here we came up with the matrix K1, which has 10 by 10, 100 elements, complex elements, and we designed this thing such that when you actually have the input over here and output, this multiplication would be this 100 elements of the matrix there. You notice, by the way, that intentionally there are some lights leaking out, and that's intentional because this matrix that we have over here is non-unitary. So of course the energy has to go somewhere, and that's our dump channel. But as we design this one, we have to make sure that the crosstalk to the other part is zero. So this for that, and then this would be for the other one that we have over here. And in fact, you can think that these two can actually operate independently. This is with the same wavelength, by the way. So this is the direction, one of the directions we are taking this to see what happens. Another interesting direction, of course, is reconfigurability and programmability. Naturally, that's one thing we would like to have over here. So there are several directions we are taking. One direction is we are looking at some of the phase change material and this guided wave structure that we have. Recently, we started a collaboration with Professor Carlos Ocampo from University of Maryland, who is expert in some of the phase change material there, and we'll see the direction it will go. Another direction we are talking about is to actually use nonlinearity naturally. What if we go back to the inverse design again, but this time we use a Kerr nonlinearity over here, such that you have a pump that's coming in, and depending on the intensity of this pump, the signal that you send over here can have a different distribution between two different outputs. So we studied this, and this is the result of our theoretical work as a function of pumped power and transmission and transmittance. You notice that when the signal comes at the port 1, output in port 1 and output at port 2 can be controlled by this power of the system that we have over here. And indeed, the design is such that the reflection of course is very, very small. And these are some of the simulation results I would like to show you. The first one shows the pump power we have, and this is the signal wave that's coming through. By the way, it's an interesting side point that I would like to bring to your attention. You notice that it's in this inverse design, when you send the signal there, the signal goes, it comes like multiple loops over there. And that's actually directly a result of the inverse design. So effectively, naturally, the inhomogeneity of this etching would give you this possibility there. And here in this, animated simulation, you notice as we have the power coming over here, this is pump power, and you increase the power, you notice how the input signal distribution between this output and that output will change. So effectively, this becomes a system that you can control like a knob by changing the pump of that. It's another direction that we are thinking about. But the more fundamental question we ask ourselves is this one. what good does reconfigurability give us? So imagine as we are following this issue of phase change material and the issue of, control with the nonlinearity, we can achieve this reconfigurability. Then what? So in order to answer that question, we said, okay, while that work we are doing like that, let's actually test how good we can do, by the way, the reconfigurability. In order to answer that question, we decided to build this system entirely in the RF. There's no light over here. It's entirely RF, 45 megahertz system. This system that you see over here consists of 25 units, representing a 5 by 5 matrix. Now, each unit, we call it a multiplier. Each unit consists of an amplifier or attenuator and a phase shifter, commercially available. This is the 45 megahertz, RF. Is this system that we build, every one of these elements can actually be controlled independently. So in other words, you can think about this, that you have a matrix 5 by 5, that every element of that you can change independently. So this is not a Swiss cheese or anything that the wave interacts. This is just independently can be controlled. Then, as we learned from our previous work, that if you get an output of this and feed it back into the input, you would be able to actually invert the matrix. And that's exactly what we did. With the waveguide system, bring it back over here, combine the signal, all of those things over here, there. So what does this do? Okay, first of all, it represents vector matrix multiplication. That's the easiest of the function it can do. And here we applied 100 different random matrices. And then this is just one example of one of those, 5 by 5 matrix that the theory and experiment. But also, if you actually have that feedback that I mentioned to you, can also invert the matrix. And that's also one example, comparison of the inverted matrix and the matrix itself there that we can see this. But the interesting point about this system is that based on what you get from the output, you can go and change the matrix and then find the inverse again. Go and change the matrix and find the inverse again. And based on that, you can repeat that. So can this system do optimization? And if I would like to acknowledge the wonderful work of my friend, Professor Eli Ablanovich, that showed that physics can do optimization. So here, this system that we build is a system that is reconfigurable, and as I show you, can actually do optimization over here. So if we have this ability that based on the output, you can go and change your system, and then that will go towards the goal you want, what interesting thing we can do. So I'm going to show you 2 toy problems, by the way, that we did in this case. One of the toy problems, imagine that you have a binomial order 5, and you would like to find the root of it. Now, it's very well known in mathematics that the way you find the root of this, you can do Newton's method. So what you do is that you start with the starting arbitrary values over here. Then based on that, you find the Jacobian of this structure, the value in that Jacobian, find the inverse of it, multiply by that, and that gives you the next iteration. And then that would go through this again. So you notice this is an example that we need to have a 5 by 5 matrix. We need to basically refresh that every time. We need to invert it. That's exactly what our gadget should do. So we decided to apply our gadget to this structure and see whether by this iteration, it's going to give us the root. And it did. It did give us the root after, this, 15 iteration. We started with some number, and then over this iteration is going to give us that. System can actually optimize, do the optimization for us. So we were very excited about this. By the way, the paper just came out, in January of 2025. And then it's okay, another thing we can do. Remember what I've said so far in my talk is that when we wanted to design those Swiss cheese, we had to do the inverse design. We ask ourselves, can the system actually do the inverse design for us? After all, what is the inverse design? Inverse design is how to have the distribution of dielectric in order to give us the goal we want. But we have to apply this to the second toy problem. And this toy problem is the following. Imagine that you have 5 scatterers over here. Imagine you have 5 scatterers, very long, dielectric rods. The locations of these rods are known. Diameters of these rods are known, but their permittivities are unknown. So then you pose this question: if I have a wave coming like this, and you would like at least 4 observation points, you would have a specific scattered wave field that you would like to have, 4 complex numbers that you would like to have at those 4 points. What should those epsilons be? That's the inverse scattering problem. It's like a radar problem. That's like inverse design problem. Can this gadget do that for us? And it did. It did. It gave us the values of those 4 epsilons there. So that's one of the reasons we put this subtitle for our paper, a metastructure that can design metastructures. That's another good example of what Eli mentioned with regard to physics can do optimization. The system is a physical system that will do optimization due to the reconfigurability. That brings me to the last item in my talk. And that is, so far, everything I've said, by the way, is a coherent system. I get to the phase. Then out of curiosity, we said, we actually have incoherent light in order to do some mathematical operations, just out of curiosity. And this is something that recently we have started looking into that. Of course, literature, is full of the various different, results in the past. I would like to mention 3 of them: the work of Nikolai Gelidel, my friend, that shows with the optical fibers how I can do, matrix multiplication. Shanhui Fan's group, and also Jason Valentine group, so that the incoherent light, they can actually do some sort of imaging. For our work, we decided to actually look at the ray optics. And one of the reasons we wanted to do that is build on what we had done in the past. I already shown you this picture many times before. But this system is a coherent system, meaning if I want to have a feedback over here, the length of this feedback is very important, because I want to make sure the phase is what I want. But if I use the incoherent light, the phase is not there anymore. So I have a flexibility over this length. Of course, another thing will give in, and that is would be limited in the sense of I can only work with non-negative real number, naturally. But of course, the system could be larger too. For example, in this system that we have several wavelength by several wavelength, if I want to do it in ray optics, I can have 100 or 1,000 wavelengths by 1,000 wavelengths there. And so that will give me that flexibility there. I don't have to worry about the length of the system. But of course, obviously, the operation will be limited. So essentially what we decided to look at is that, okay, what would happen if I have 3 input? Then I use a beam splitter, standard beam splitter. I can split it. And this beam split, the ratio of the split is under your control. And then here you're going to combine this as a beam combiner. And then, of course, you can bring the wave back. And that system would have that feedback I mentioned to you. But this time, phase information is not needed. It's lost. We don't even need that. So we decided to study this just theoretically in order to see whether that would be possible. One of the motivations we have is that some of the mathematical operation, obviously not all of them, but some of the mathematical operation with incoherent light and ray optics that significantly simplify the system. So rather than using laser, I can just use LEDs. Rather than using something specifically with the Swiss cheese design with a specific length, I can use the optical fiber, for example, and so on. So we decided to study this, and I'm going to go through and then I stop. So in order to do the feedback, obviously, conceptually, you can use mirror. In order to have, you can have a beam splitter with the ratio of T1 and Y minus T1 division, and then beam combiner over here, and you can have 2 different paths. Anyway, going through all these, standard, ray optics value, you have this matrix. Now, obviously, this matrix is non-negative real, all of it. And so the question is, if this represents this matrix over here, can I invert it? And the answer is yes. Actually, we can. By bringing those mirrors and so on back. So here, in this simulation that you see over here, this is basically, quote-unquote, time. Of course, time, what does that mean, time over here? Obviously, this is ray optics and it goes with the speed of light. But what we're saying is, as it goes and iterate over here, we keep track of that process. So time really needs data. And you notice after the very quick iteration, it gives to the value that represents the inverse of unity minus A matrix. And the same thing for the other channels. So indeed, this system can invert the matrix, albeit a matrix that is non-negative real. And then we decided to extend it to 3 by 3, similar idea, except it's just a little bit more complicated. We have more beam splitter, beam combiners, and so on that we have over here. And indeed, by the way, you notice that the degrees of freedom can increase. Here, for example, we are just using the beam splitter with the ratio of T1, T, so on. But you can put an attenuator along this line, and you can do that. Anyway, this is one of the directions that we are pursuing to see in what interesting advantage this system may have. Let me just show you an interesting, animation over here. This animation did it in console as to follow the ray of lights. This is ray optics, no phase information at all. And that system, as it goes through this, is going to actually do the inverse of that system here. So that brings me to the end of my talk. I want to thank all the members of my group and collaborators that I had the privilege to work with. I'm very thankful and grateful to all of them. And I'm very thankful also to the organizer of this conference and to all of you for your interest, and I'd be happy to answer any question you have. Thank you very much.